It's yellow today, I guess. Stick with yellow. All right, let's get started. Okay, so last time, let me make sure this is on. Okay. Last time we proved distributional JL. We showed that, well, we focused mostly on epsilon being less than 1. So the max of these two is 1 over epsilon squared. But we showed if you map into 1 over epsilon squared log 1 over delta dimensions with a random matrix, like a random sign matrix, you're scribing for today, right? Okay. You'll have that for any vector x of unit norm. This is vectors in the unit sphere. With high probability, you'll preserve the norm of x. So you'll preserve it up to epsilon with probability 1 minus delta. Your failure probability is delta. And we saw in the lecture before that this implies JL. JL says that for any set of finite points, you can map to a dimension that only depends logarithmically on the number of points and preserve all the distances up to 1 plus epsilon. Okay, so this is JL. Today, I want to talk about a couple things. So today, I want to talk about lower bounds. I'll state a few. I'll only prove one. And these lower bounds are going to be of the form, let's say for JL, we're going to show that there exists, for any n, for any capital N, there exists a set of capital N points in L2 such that any embedding requires roughly that m up to a small factor. Okay, so we're going to show that the JL lemma is almost optimal. Okay? But that's worst case optimality. It means there is a hard set of vectors. Okay? So the second thing we're going to do is go beyond worst case. Right, that's kind of a worst case analysis kind of lower bound. There is an input that's hard. Right, but if you're actually doing, if you want to actually do dimensionality reduction on some database of vectors that someone gave you, maybe you want to do as well as you can do for that database. You don't want to compare yourself against a worst case lower bound because your data is not a worst case instance, right? And this is going to be something called Gordon's theorem. And later in this course, when we start talking about numerical linear algebra or dimensionality reduction for linear algebra problems, as well as compressed sensing, you're going to see that some of what we're going to want to do is basically we want a JL kind of dimensionality reduction for an infinite set. So for example, for an entire subspace of Rn, or for the set of all sparse vectors in Rn. So these are infinite sets of vectors. And then log the number of points doesn't make sense anymore. That's infinite. But Gordon's theorem will be able to tell us immediately how many dimensions you can get away with to do dimensionality reduction on that set. Okay? Yeah, so I want to talk about these two things and kind of, in order to appreciate Gordon's theorem, I'm going to spend a little time. So let's call it 1.5, which actually goes a little bit before Gordon. I'll say something about bounding suprema of Gaussian processes. I'll say more what that means when we get there. But it's just a little preliminary stuff I should cover just so that you can appreciate some of the terminology I'm going to be using in Gordon's theorem. Okay. Okay, good. So let's start off with lower bounds. Okay. Good. So the first thing I want to say is what about, so there are two different problems here. There's distributional JL and there's metric JL, and there's JL, okay, the thing that's usually called JL. It's good to keep in mind that these are two different problems. A lot of the literature out there just says JL, and they could mean either one of these depending on the paper. But they are different problems, and one of them is resolved, and one of them is still unresolved. Okay, so it's good to keep in mind that there are open problems here. So let me first talk about distributional JL. Okay, so you can show that for all. So this is due to first due to J-Ram and Woodruff. And then there was a proof also by Kane, Mecca, and myself. Okay, which says that any epsilon delta DJL distribution for, let's say, epsilon delta between 0 and 0.5 must have m being at least the min of n and 1 over epsilon squared log 1 over delta. Okay. I don't want to go into the details of the analysis, but I'll give you like a proof sketch. So I'll show you the proof sketch from here. This work, it doesn't quite get this up to n, but it gets almost there. And I think it's shorter to give the sketch of this one. So let me just give a sketch. Okay. So it's going to be something like what you saw actually in one of the communication complexity lower bounds. So it looks something like this. What does DJL tell you? DJL says that for all x, the probability over pi that pi x squared minus 1 is bigger than epsilon is at most delta. Right? That's what DJL says. Well, if it's true for all x, then it's true for any distribution over x's as well, right? So this implies that, for all distributions mu on the sphere, we have that the probability over x drawn from this distribution of the probability over pi of that same thing is at most delta. And then we can swap these two probabilities, right? So this implies that the probability over pi, the probability over x coming from mu, pi is being drawn according to this distributional JL. But if a random pi has this probability of being small, right, it means that there exists a pi in the support of the distribution where this probability is small. This implies that there exists a pi in the support of the distribution such that the probability over x coming from mu is less than delta. Right? And then basically the way that now you have to do some calculations, but the way the analysis goes is you say, look, if pi only has m rows, so first of all, pick u to be uniform distribution on the sphere. And then what you argue is you say, look, if you take any fixed matrix pi with only m rows, then it's not going to be able to preserve a random vector on the sphere unless m is at least 1 over epsilon squared log 1 over delta. I mean, that's just that requires some analysis, but that's the sketch of the proof. Okay? So I'm not going to do the details here. Good. So this is, I don't want to write QED because I didn't actually prove anything, but this is roughly how the proof goes. Okay. So 2 is JL. So that's roughly how the lower bound for DJL goes for distributional JL. How about lower bounds for JL? Right. So distributional JL, you have to pick a random matrix kind of independently of the vector, and it has to work for any vector. A random matrix has to work with high probability for that vector. JL is a different problem, right? In JL, actually, I shouldn't even write it this way. The way I wrote JL, so there exists, let's say a function mapping x to L2M. And let me say that for all x, for all xy and x, if you look at f of x minus f of y, this is equal to 1 plus or minus epsilon x minus y. So let me. Okay, so what JL, the original statement of JL in their paper looked like this. For all subset of L2, there's a function which maps that subset into m-dimensional space that preserves distances. It just so happens that, when you prove JL, that function f is linear, right? Because how do you prove JL? Well, the ways that we know how to prove JL right now use DJL. And DJL gives you a linear map, right? But you could, if you're happy to have any map, then you can state JL this way. And the proof happens to give you a linear map. So JL, let's say that you insist on f being a linear map. F of x is pi x for some pi. Okay? Let's suppose you insist on that. Then there's a lower bound. Let me just mention, yeah, the difference between JL and DJL. DJL, you have to pick pi independently of the point set, and it has to work with high probability. JL, F is allowed to depend on the point set. For all point sets, there exists an F, right? So you're allowed to look at the point set and then come up with the best F you can for that point set. Right? It just so happens that the proofs of JL we have now don't do that, but you are allowed to do that. Okay? So if you insist on the map being linear, then I have some work with Casper Green Larson. It's on archive to manuscript. It says that M has to be at least the min of n and 1 over epsilon squared log n. Okay? So there is a hard point set. There is a point set that any linear map which preserves it needs at least this many dimensions, which is tight, because you can always achieve that with the identity matrix, and this you can achieve with JL. Okay. And we're going to actually revise our manuscript to have a different proof. But now that you know this, actually, there's a quite simple proof of this fact, which basically goes as follows. It's going to be via the probabilistic method. We're going to show that there exists a hard set of vectors. Well, how do you do that? We know that from here, if you take a fixed matrix, right, a fixed linear map, the probability that it preserves, if it doesn't have enough rows, it's not going to preserve a random Gaussian vector with high probability. Okay? So the hard set here is basically take like a bunch of random Gaussian vectors, and you want to preserve all their distances, even their distances to 0. You want to preserve their norms. Well, this matrix doesn't even preserve one of them with good probability. The fact that it preserves all of them is quite small. And then you basically do a union bound over all matrices pi to say no pi works. There's a little hitch there, which is that there are an infinite number of pi's. So what you do is you take a net over all the pi's, and you argue that no pi in that net, in that finite net, works. And then you use that to imply that if no pi in the net works, then no pi at all works. Okay, good. So that's a lower bound for JL if you insist on F being a linear map. What about if you don't have any requirement on F? And that's what I'm going to show today. So 3 is JL. F can be anything. And then No-Go Alon showed in 2003 that M has to be at least the min of n and 1 over epsilon squared log n over log 1 over epsilon. So there's an open problem here, and the open problem is basically remove this. Right, so open is remove this. Remove this log 1 over epsilon. Yeah?
So is what you said the only difference between DJL and JL? Like in JL you can actually look at the input, whereas in DJL you...
Yeah, so yeah, that is the difference. So in DJL, first of all, DJL isn't even about a collection of vectors. DJL is, I just want to come up with a distribution that works for any fixed vector with high probability. JL is, or JL, I guess, is a lemma that answers the following question. So the question is, I give you a set of vectors, reduce them to the lowest dimension you can while preserving their distances up to 1 plus epsilon. The JL lemma provides a solution to that problem. And it provides a solution to that problem where the target dimension is this m, 1 over epsilon squared log capital N. Okay. And it happens to provide it with an embedding that's linear. Okay. But you could ask that dimensionality reduction question without insisting that the solution be a linear map. Okay, and to this day, no one knows how to take advantage of that. But conceivably, you could take advantage of using nonlinear maps to do better than JL. You're not going to do much better because there's a lower bound, but potentially you could save something. Okay, and I'm going to prove this lower bound for you. It's actually quite a short proof. But there's an open problem to remove that. So Alon's lower bound goes something else like as follows. So it's based on something that you've already seen, I believe in PSET, maybe 1 or 2. I think PSET 1, which is incoherent vectors. Okay. So suppose in JL, suppose your x there is 0, E1 up to En. So it's 0 as well as the standard basis vectors. Okay. And kind of distances are invariant under translation, right? If I have an embedding and then I just translate all those vectors by the same amount, then the distances stay the same. So without loss of generality, f of 0 is 0. Just translate everything by f of 0. And also write f of ei as vi. Okay. So this implies that f acts as this matrix v1 vn on x. Right. Okay, what can you tell me about these VIs? First of all, what can you tell me about the norm of VI? Right, so remember, I have to preserve distances between these pairs of points. So in particular, I have to preserve distances to 0. Right? What is f of ei minus f of 0? Right? That's just vi. Right? I translated everything so f of 0 is 0. This is just vi. But we said that the norm of f of x minus f of y has to be roughly the norm of x minus y. So this thing has to be roughly the norm of ei, which is 1, right? So this thing is 1 plus or minus epsilon. Okay. Also, for all I not equal to j, if you look at vi minus vj L2 norm squared, right? Just remember, the L2 norm squared of a vector is that vector dotted with itself. So if you expand that out, this thing is equal to vi squared plus vj squared minus twice the dot product of vi and vj. But vi minus vj should have roughly the same norm as ei minus ej. That's the JL guarantee. So this right here is 2 plus or minus epsilon. Right? This right here is 1 plus or minus epsilon. This right here is 1 plus or minus epsilon. Right? So that implies that the dot product vi dot vj, if you move things around, cancel this 1 plus 1 with that 2, and divide the 2, this dot product is O of epsilon. Right? So basically any embedding, right, and the number of rows of this matrix is exactly m, where f is mapping from x into L to m, right? So when the number of vectors is n. So what this is telling us is, if you have an embedding for this set of vectors, this is going to be our hard set. If you have an embedding for this hard set of vectors, then it implies that you have a set of incoherent vectors that all have roughly unit norm and whose dot products are all roughly epsilon. Okay? And in fact, we can do this, set Wi to be Vi over the norm of Vi. This implies that for all I, Wi is 1. And also for all I not equal to j, we still have that Wi dot Wj is O of epsilon. Okay? So this is exactly the definition of incoherence you saw earlier in the course when we were talking about deterministic point query and deterministic heavy hitters and on your p set. So all we need to show is that you can't have too many incoherent vectors in low dimension. It's just not possible. That would give a lower bound. That would say that if you want to have lots of incoherent vectors, if you want to have n of them, then your dimension has to be large. Right? That's what we're going to show. So call this matrix pi. This is our JL matrix for the simplex. Define A to be pi transpose pi. Okay? Notice that the rank of A is at most m. What does A look like, by the way? Right? It's an n by n matrix. The diagonals, every entry is just a dot product, Wi dot Wj. Well, actually, I shouldn't say pi. So this is basically pi with the Wi's. Okay. So let me write like this. So pi is this matrix now I'm defining. W1 up to Wn. So pi transpose pi, each entry is some Wi dot Wj. So the diagonals are all 1. And everything that's off the diagonal is plus minus epsilon. So it's like an almost identity matrix. And then what Alon says is that any real symmetric A, which is epsilon near to the identity. By epsilon near, I mean looks like this. Must have its rank being at least the min of n and 1 over epsilon squared log n over log 1 over epsilon. That's really how Alon's lower bound goes. Yeah, question? Why is the rank less than m? Right, so of A. Yeah. So what do we have? We have that A is equal to pi transpose pi, right? Which is equal to, how should I write this? So sum of rho. So in general, whenever you have A transpose B, it's equal to the sum over I, AI, BI transpose, where A looks something like A1, A2, etc., and B looks like B1, B2, etc., right? So let's call these rows pi 1 up to pi m. Then this thing is equal to the sum I goes from 1 to m of pi I transpose. Right, so we've just decomposed it into a sum of m rank 1 matrices, so its rank is at most m. Okay, good. So that's what we're going to prove. Before we prove it, we're going to need a weaker version of the lemma, and then we're going. Yeah, question? Okay.
I thought we're proving for f can be anything.
Yeah.
F linear here.
Yeah, so that's the beauty of this hard set x. Any f for this x automatically implies a linear f for this x by this trick, right? Whatever f you give me, translate all the embedded vectors so that f of 0 is 0. Just subtract f of 0 from every vector in the image of f. That doesn't change anything about the distances. And then now, just define a matrix whose ith column is exactly f of ei. Then this matrix acts on x exactly as f did. Yeah. So I mean, in general, whenever your hard set of vectors is linearly independent, you can without loss of generality, you can assume f is linear. So Alon's hard set is a linearly independent set. Okay. So before we prove Alon's thing here, we're going to prove, this is how he did it, so we're going to prove Alon minus, okay, which is pre-Alon, okay, which says that any real and symmetric A, which is 1 over root n near the identity, must have rank R, which is at least omega n. Okay? So we're first going to prove that, and then we're going to show that we can then kind of bootstrap from this and get the real thing that we care about. So let's prove this. So whenever you have a real symmetric matrix, you can diagonalize it and you have eigenvalues. Okay, so you have real eigenvalues. So let lambda 1, lambda n be the eigenvalues of, and actually let me just even say lambda r be the non-zero, r is the rank here, non-zero eigenvalues of A. Okay. Now, on the one hand, we have that the sum of lambda I squared, I goes from 1 to r. So what's one way you could calculate this? So maybe I should just say it. I don't know if people are, maybe this linear algebra is not on top of your fingertips, but so the sum of lambda I squareds is always equal to the Frobenius norm of the matrix, the sum of the squared entries of the matrix. Okay. So this is just a linear algebra fact. Well, it'll follow from something we'll see on the next line. Okay. So this thing is equal to, well, what is the Frobenius norm squared? All the diagonal entries give you n. They give you 1 each. There are n of them. And then there are n times n minus 1 off diagonals. They each give you at most epsilon. So this is at most n plus n times n minus 1 epsilon squared. Okay. The next thing is, if you look at the sum, let me write it this way, the sum over I from 1 to r of lambda I, okay, then by Cauchy-Schwarz, first of all, what is the sum of lambda i's? Another linear algebra fact, right? This is just the trace of A. It is equal to the trace of A, which is equal to n. Okay? And this thing, by Cauchy-Schwarz, is at most root r times the sum of lambda I squared to the 1/2. Right? And so in general, the sum of AI bi is at most the L2 norm of A times the L2 norm of B. So AI is lambda I, bi is 1. Do a Cauchy-Schwarz. And then now square all sides and then divide through by r. This implies that sum of lambda I squared, I goes from 1 to r, is at least n squared over r. And then now you just move things around. Okay? So you have that sum of lambda I squared is at most that, and it's at least that. That implies that n squared over r is at most n plus n minus 1 epsilon squared. Divide the n's. This implies that r is at least n over 1 plus n minus 1 epsilon squared. But for me now, what was epsilon? Epsilon was 1 over root n. So 1 over root n squared is 1 over n. So this is just omega n, right? Because epsilon was 1 over root n. Right, so right, the way to see this also is the Frobenius norm squared is just the trace of A transpose A. And the eigenvalues of A transpose A are just the old eigenvalues squared. So anyway, okay, good. So we have Alon minus, and now we want to get the true lower bound over here. So now I want to prove this thing. Okay. So this is what we're going to do. So define, let's call it AK to be the matrix where AK ij is just aij to the kth power. We're not taking the matrix to the kth power. We're entry-wise. We're taking every entry to the kth power. Okay. Claim if the original matrix A had rank R, then A to the k, the rank of AK is going to be at most r plus k minus 1, choose k, or something like that. Maybe k minus 1. Yeah, choose k. Okay. So what are we going to do? Our RA is epsilon near the identity. All the entries off the diagonal are at most epsilon. If we raise epsilon to a sufficiently large power, then all the entries will be less than 1 over root n, which will imply that the rank of that resulting matrix is omega n, right? So let me defer the proof of this claim, and let's just see what this claim gives us. Choose k to be something like the ceiling of log base 1 over epsilon of root n, which is basically something like 1/2 log n over log 1 over epsilon, up to an additive 1 or something because of the ceiling. Okay. Then epsilon to the k is at most 1 over root n. That's why I chose that k. That implies, right, the fact that now this is a 1 over root n near identity matrix implies that well, what's the rank of this matrix? The rank of this matrix is at most that. That implies that r plus k minus 1, choose k, has to be at least some constant times n. Right? That's what Alon minus gave us. And then you basically just calculate. I mean, from here it's straightforward. So now you just say, well, you always have, a fact is you always have that n choose k is at most en over k to the k. This is just a useful estimate to keep in mind, and it's always like at least n over k to the k. So we're going to use the upper bound. This thing is at most that. So what we have is that e r plus k minus 1 over k to the k is at least some constant times n. Take logs of both sides, and then you get that k log of e r plus k minus 1 over k is greater than or equal to log of Cn. Okay, and then I'll leave it to you as an exercise. This is basically now just a bunch of calculations. Okay, so remember what k is, and then move things around. Yeah.
Sorry, why is the rank of a to the k less than equal to r plus k minus 1?
All right, so that's a claim, which we're going to prove right now.
Oh, excellent.
Yeah. So, right. So this is a claim which we're going to prove right now, and then given that this claim is true, we can complete the proof of Alon's lower bound. Yeah. So now we just need to prove the claim. Now we just need to prove the claim. So we're all on the same page. Sorry. Okay. Okay, so say that the rows of A are A1 up to AN, and let, let's call them T1 up to TR be a basis for the row space of A. Okay? Which implies that for all I, there exists some alpha in RR such that AI is equal to the sum j goes from 1 to r. Let me say, let's say q goes from 1 to r, alpha q, tq. Right? So every row is a linear combination of the basis for this row space. So what happens when we take A? What happens when we do this k operation on A? Right? So AK ij is just equal to AI to the j, or to the k. It's equal to aij to the k. Okay. Wait, let me make sure this is parsable. So take the vector AI, look at its jth entry, raise that to the k. Which means take the jth entry of this vector and raise that to the k. So this is equal to the sum over q of alpha q tq j raised to the kth power. And then just expand this thing out. Right? Imagine now writing this as a sum of lots of monomials. Oh, yeah? Question? All right. And what does this thing look like? This thing basically looks like right? So when you expand this out to the kth power, you're going to have some q1, q2 up to qk, and you're going to have a product of a bunch of alpha q's and then a product of a bunch of tqj's. Right? So this is going to look like a sum over, let's call it q1 up to qk, product z goes from 1 to k, alpha qz, times a product of tqz j to the k. No, not to the k. Okay. And then now imagine grouping the q's together that are equal, right? So it might happen that q1 is equal to q3 is equal to q7 or something. Imagine grouping the ones that are equal. So we can sum over how many distinct q's are in a particular monomial. So sum over, y goes from 1 to k. Then y is the number of distinct q's. And then the sum over, let's say, q1 is less than q2 is less than qy. Here you'll have some multinomial. Let's also sum over how many of each we take. So sum over d1 up to dy, such that d1 plus dy is equal to k, and for all z, dz is at least 1. Basically, these are the exponents of the q's. How many times did we take each q? And then there's some multinomial coefficient, which is k choose d1 up to dz, times some product of some alphas, times a product of t's. Okay. So don't worry about, I mean, the point is I'm just summing over like all possibilities for how many of each q there are. Okay? And then the takeaway is this part right here. Okay. So create a collection of vectors S1, S2, etc., whose entries look like. So these are going to be the same dimension. They're going to be n-dimensional vectors, just like the t's were. Their entries look like, like that, basically. The product, this goes from z goes 1 to y, sorry. The product z goes from 1 to y of t, qz, j, or this is now 1 to the dz. Product t, qz, 2 to the dz, etc. Look at all vectors that look like this. Okay? What we just showed is that any row, basically any ith row, any row of this kth power, not quite power, but k thingy operation on A, is a linear combination of vectors that look like this. With some, there's some coefficients that depend on multinomial coefficients and products of alphas and whatever, but they're all linear combinations of vectors that look like this. right? Such that the sum of the dz's is exactly equal to k. So now the question is just, how many vectors are there that look like this? Okay. So I claim that the answer is r plus k minus 1 choose k. Okay. And if you haven't seen this before, it's a pretty simple argument. I'll show it to you. It's just a bijective argument. People sometimes call it stars and bars. At least I think that's what when I saw it in my discrete math class, that's what our professor called it. So the basic idea is as follows. Imagine having k zeros. And then now, imagine putting dividers between the zeros. So imagine having r plus k, or let's say r minus 1 dividers. Okay. So I'll put a divider here, and I can put the dividers wherever I want. I can also put a divider at the beginning, like this, something like that. Let's say there are r minus 1 dividers. And by a divider, I just mean a 1. Okay. Everything to the left, basically, the number of zeros to the left of the first divider tells you the power that I'm going to give to T1. So this is going to be like, I'm raising T1 to the number of zeros. And here's like I'm raising T2 to the number of zeros, etc. Right? So what this sum is doing is it's asking how many ways are there to choose basically all the powers of these t's so that they sum up to k. And that's exactly in bijective correspondence with the number of ways of writing down these zeros and dividers. But how many ways are there? This is just a binary string which has a total of k plus r minus 1 digits. And then you have to choose which of those digits are zeros and which ones are ones. So you have to choose k of them to be zeros, and the rest will be ones. So that's exactly r plus k minus 1 choose k. Okay? So that's it. Okay, so good. That's it for JL lower bounds. And now let's move on to beyond worst case analysis, right? So remember, Alon's lower bound, yeah, question?
I don't entirely follow. After you get that claim, why exactly does Alon follow?
After you get this claim? Because we have Alon minus, right? Which tells us that, well, I erased it, but, oh no, there it is. Alon minus tells us that if epsilon were actually 1 over root n, so all the off diagonals are at most 1 over root n, then the rank has to be linear, right? So what we're doing is we're taking our original matrix. The off diagonals aren't 1 over root n, but they're epsilon. And we're just entry-wise powering this matrix until it's below 1 over root n. And then now the resulting matrix must have rank linear. But the question is, what's the rank of the resulting matrix? If the original matrix had rank r, the resulting matrix has rank at most this. Therefore, this must be at least n. So this is at least n. That gives us a lower bound on r. Yeah. Okay. So that's the proof. Okay. So we're done with a JL lower bound. But remember, this is a worst case lower bound. Right? This is telling us that there exists a hard set of vectors. But maybe this, as I said in the beginning of lecture, maybe the vectors that are in front of me aren't so hard. So can I get some better worst case understanding? Or beyond worst case understanding? Like instance-wise good bounds. Okay. So let me reformulate. So we're given some t, which is a subset of the unit sphere. for example, T is the set of all vectors x minus y, or normalized to have unit norm. Like in JL. We want that for all x and t, pi x L2 norm squared minus 1 is less than epsilon. Right? That's what we want. Okay. And maybe what we want is, basically pi is random, so we want that the probability over pi from some distribution that the sup over x and t of pi x squared minus 1 bigger than epsilon is less than delta or less than something. Okay. So So we're going to do exactly that. Let me make sure I say the correct reference. Yeah. So theorem. And the original paper was due to Gordon back in '88. Okay. But then there have been subsequent improvements. So there's Clartog and Mendelssohn. And there was also Mendelssohn, Pajor, and Tomczak Jaegerman. In '08, and there's also, you can see a paper by Dirksen in '14. Okay. Which says that suppose, so this is I usually refer to this as Gordon's theorem. People say Gordon's escape through the mesh theorem. It says, suppose pi ij is, plus minus 1 over root m. Okay, so like the same kinds of JL matrices we were looking at before. In fact, even JL, as we described before, like we use the Hansen-Wright inequality, right? Which I proved for sines, but it turns out there are references. So for example, if you look in the lecture notes, there's a reference to a paper by Rudelson and Verschinen, but there are other analyses as well that says you don't even need sines. You just need any distribution that decays at least as fast as a Gaussian, has mean 0 and variance 1. Okay? If you take that distribution divided by root m, it'll give you distributional JL. So when I say decays at least as fast as Gaussian, sines do that because sines have awesome tails. The probability that a random sine is bigger than 2 is 0, right? So they decay like super well. Let me just write it down for sines. Suppose that you have pi j being this, and you have m being at least, let me write it down, then I'll tell you what it means, g squared of t plus 1 over epsilon squared. Actually, let me write plus log 1 over delta over epsilon squared. Okay, then star holes. Okay, so if you want to preserve all the vectors in T, it's enough for M to have this number of rows. Okay, what is G squared of T? Definition: the Gaussian mean width G of T is defined to be the expectation over a Gaussian vector of the sup x and t of g dot x. Okay. So, for example, if all the vectors in T are orthogonal vectors, so G is just a vector of independent Gaussians. They all have mean 0 and variance 1. Just to get a feel for things, suppose your set T looked like this. You had the standard basis vectors. Right? Then G1 dot this x is just G1. G dot E1 is just G1. G dot E2 is just G2, et cetera. So you're asking what's the max of G1, G2 up to Gn? Okay. The max of those Gaussians you can prove is root log n. Okay. So we'll see this in a second. I'll do something more formally in a second. But in that case, you'll get root log n. And then G squared becomes log n. So basically, this thing is always, it's never worse than JL. It always says you never need more than log t dimensions to embed t, just like JL would say. But if your vectors are nice, for example, imagine t just looked like vectors that are all basically pointing in almost the same direction, right? Then if you take g dot this vector and g dot that vector, they're actually heavily correlated. And you can say, like, the max of g dot these x's is going to be a constant. And then you can get away with better dimension. I mean, a trivial example is imagine T is a multiset with just the same vector over and over again. Then the sup over x and T of g dot x is just g dot whatever that vector is, right? And the expectation of g dot that vector is 0, actually, right? So this just says 0 plus log 1 over delta over epsilon squared. So it doesn't even depend on the size. So the more clustered, the more well clustered your vectors are, the better dimension you can get away with. So this is a beyond worst case kind of statement. The answer depends on T. If T is nice, you do better. Let's just make this. Let me just give you a little feel for things. So claim for all t subset of unit vectors, g of t is at most square root up to a constant square root log n, where n is the size of t. Okay. Proof. Define. Okay, so let's say t is the set of vectors x1 up to x capital N. Define zi to be the dot product of g with xi. Right. So g of t is the max of z1 up to zn. Question?
Apply symbol G again.
Oh, G is a vector of Gaussians. So T is a subset of vectors in Rn, and G here is a vector of Gaussians, G1 up to Gn. Independent Gaussians of variance 1, mean 0 variance 1. So G of t is the expectation over G of the max of these things. In general, well, let's actually just write, let me actually even just put absolute values here. So these are all non-negative. So G of t is at most this, right? And whenever you have the expectation of a non-negative random variable, it's the integral of the tail bound, right? The expectation of z, if z is non-negative, is the integral of the probability that z is bigger than u du. So this is equal to the probability, or the integral, from 0 to infinity, the probability over g that this max z1 up to zn is bigger than u du. Let me break this integral up into two pieces. This is equal to the integral from 0 to root log n of the probability plus the integral from root log n to infinity of that probability. Okay. Probabilities are never bigger than 1. So this and there's du. So this probability is at most 1. So we're integrating something that's at most 1 up to root log n. So this thing is at most root log n. Okay. Also by a union bound, a probability that so what does it mean that the max is bigger than u? It means that for all I, zi is let's see. So the probability the max is bigger than u means that actually, and I should no, this is fine. So this is equal to the probability that there exists an I such that zi is bigger than u. Right? And the probability that there exists an I is at most the sum over I by a union bound. This is at most the sum over I probability that zi is bigger than u. So this whole thing is at most n times e to the minus u squared over 2 du. Right, this is how a Gaussian tail-bound behaves. And because we started our integration at root log n, let's even put it as square root of 2 log n or something to basically kill this n. E to the minus square root 2 log n squared over 2 is 1 over n, which kills that n. So this whole thing overall is root log n plus a constant. So this whole thing is root log n. So this thing is always at least as good as JL, but it can be better. Okay. Question? This? So, this is this probability, the probability that the max is bigger than u, is to say that there exists. This is the probability that there exists an I such that zi is bigger than u, right? And that means that either it's the probability that z1 is bigger than u, or z2 is bigger than u, or z3 is bigger than u, etc. And the probability of a bunch of ors is at most of some of the probabilities by union bound. And the probability that zi is bigger than u, well, zi, what is zi? Zi is g dot x, I. But if you take a Gaussian dot with a fixed vector, it's a Gaussian, right? And it's a Gaussian of variance, the square root of x, which is 1. So what's the probability that a Gaussian is bigger than u? It's basically something like e to the minus u squared, roughly. Okay. So, and there are n things that we're summing up, capital N things. So this probability is at most capital N times e to the minus u squared. And then you integrate it over u, which is, again, something like e to the minus u squared. OK, so long story short, this thing is always, it's never worse than JL. It's always at least as good as JL, because you can always get this to be at most log capital N. But for some point sets, it's better. So now let me say a little bit about 1.5. I'll inject something into the notes, but I don't want to spend too much time on it in class. So I'll just give you a little taste of it. want to understand some way of writing g of t, or is there an equivalent formulation of g of t? Okay. So you can come up with various upper bounds. So, so now let's do 1.5 over there. So this is how to bound g of t. And so, one possibility is take 1, let's say, is just to say g of t is at most square root log the size of t. Let me write it like this. Square root log to the 1/2 of the size of t. Right? That's what we just proved. It's never bigger than that. Take 2. Let t prime, subset of t, be such that for all x and t, there exists an x prime and t prime with x minus x prime is at most epsilon. Suppose we had such a t prime. This implies that g of g dot x is equal to g dot x prime plus x minus x prime. I just added 0 in a funny way, which is equal to g dot x prime plus g dot x minus x prime. And this thing is certainly at most the norm. Whenever you take the dot product of two vectors, it's at most the product of their norms. This is at most epsilon times the norm of g. Okay? Which implies that g of t is at most g of t prime plus epsilon times the expectation of the L2 norm of g. Right? But this thing here is at most, so in general, the expectation of z is at most the expectation of z squared square root. So this is at most the expectation of g squared square root. What's this expectation? What's the inside expectation here? Right, this is g1 squared plus g2 squared plus dot 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 plus gn squared. The expectation of gi squared is 1. So this inside here is little n, it's the dimension. So this is root n. Right, so this is equal to g of t prime plus epsilon root n. So another way to get a bound on g of t is to take a very fine net, an epsilon net of t, call that t prime. By a net, I mean a set of vectors such that everyone is close to it. Okay. And then we get this bound. Why is this good? Because if the vectors in T are very well clustered, if they're all, they're n-dimensional vectors, but maybe they're all like really near each other, then there's a small t prime that covers everyone. So instead of paying, so here now, and finally what we can say is this thing here is at most root log the size of t prime plus epsilon root n, right? Because in general, g of t is never bigger than root log t. So if the vectors in T are well clustered, the size of t prime is way less than the size of t. So this is better, and we need to just drive epsilon to be small enough, take a fine enough net such that this term doesn't matter. That's another way to go about things. Okay. And let me write two more ways to go about. So these are going to be progressively better and better ways of bounding g of t until we get to the best way. So take 3 is basically take 2, but just with a slightly better, slightly more sophisticated thing, which is take T0, subset T1, subset T2, subset T, such that TR is a 1 over 2 to the R net of T. And write that X is equal to X0 plus X1 minus X0 plus X2 minus X1 plus da, da, da. Write an infinite sum. And this thing telescopes, and eventually you just get X. So this implies that g of t is at most the expectation of g dot x0. Well, let me write it like this. This is, this guy is in t0, this guy's in t1, etc. This is at most g of t0 plus, which is at most root log the size of t0, plus the sum r goes from 1 to infinity of root log. So question, how many possible difference vectors are there x1 minus x0? Right? So g of the sup over all x0s and t0 of g dot x0 is at most root log the size of t0. Right? Root log the number of possible vectors that could be here. How many possible vectors could be here in this difference? It's the size of t1 times the size of t0. Right? How many difference vectors are there of this form? It's the product of the two set sizes. So root log the size of tr times tr minus 1. Okay. And by the triangle inequality, what's the norm of this vector? Right? What's the norm of the vector xr minus 1? Well, by triangle inequality, it's at most xr minus x plus xr minus 1 minus x. This is at most 1 over 2 to the r. This is at most 1 over 2 to the r minus 1. So this is at most 3 over 2 to the r minus 1. Or, this is the same thing as saying 6 over 2 to the r or something like that. So I can put a 6 over 2 to the r here. So in general, I guess what I should say is, really in general, what you really can get is g of t is at most the radius of t times the norm of times root log the size of t. So this statement follows from the same calculations here, right? So, just think about it. So if you have a set of unit norm if you have a set of vectors whose L2 norms are all at most alpha, just scale all the vectors by 1 over alpha, right? So now they all have unit norm. And this tells us that their mean width will be at most root log the number of vectors. So if you unscale by the 1 over alpha, you get alpha times root log. So in general, if all the vectors have norm at most alpha, then g of t is at most alpha times root log. And all these vectors here, all these vectors of the form xr minus 1, have norm at most 6 over 2 to the r. So we can get this. And notice also that the size of a coarser net is smaller than the size of a finer net. So the size of tr minus 1 is at most the size of tr. So this thing here is at most the size of tr squared. But log of something squared is at most twice log. So up to a constant, this thing is at most root 2 times square root log of the size of tr. so that implies that g of t is at most up to a constant, kind of the sum r goes from 0 to infinity, 1 over 2 to the r times root log the size of tr. And this is often written as sum r goes from 0 to infinity, 1 over 2 to the r times root log, I'll define this in a second, t L2 1 over 2 to the r. So this number n is basically what n just is what's the size of the best epsilon net for that point set under this metric. So this means what's the size of the best 1 over 2 to the r net for t under the L2 metric. That's just the size of tr. Okay. And often this is written, this is bounded by an integral. The integral from 0 to infinity of root log t L2 u du. This is usually called Dudley's inequality. So this is take 3. Okay. And I'll just write take 4 without actually proving it, but I'll put the proof in the notes in case you're curious. So take 4. Write S0 subset of S1 subset of subset of S, F subset of T, such that the size of S0 is 1 and the size of SR is at most 2 to the 2 to the R. And define, OK, then can show that the Dudley bound, take 3, is the same up to a constant factor, is theta of the inf over all sequences SR satisfying this thingy here. Okay. So you can prove that this bound here is up to a constant equivalent to this bound here. Okay. I'm not going to prove it for you, but the basic idea is here I wanted a 2 to the r net. So this r and that r are basically not the same. So maybe so that it's not confusing, let me say the sum from S goes from 0 to infinity. So here, for each r, I insist on having a 1 over 2 to the r net. And I want you to make the net as small as possible. Here, it's sort of just an inverted way of looking at it. I tell you the size of the net that I'm allowing you. So the sth net is allowed to have at most 2 to the 2 to the s points. And using this number of points, I want you to minimize this, right? I want you to choose these s's to minimize the maximum distance to each s. Right? You want to minimize the sup over x of this, which means make capital S the best net you can make using 2 to the 2 to the little s points. Right? And you can show that kind of these two formulations are equivalent. And then take 4 is define something called gamma 2 to be the inf over these s's of the sup over x of the sum 2 to the s over 2 times the distance in L2 from x. So basically define gamma 2 to be the same thing, but where you pull the soup outside. Okay. And theorem, so the upper bound is due to, the lower bound is due to Talleyrand, and the lower bound is due to Fernique. G of t, for all t, G of t is basically equal up to a constant to gamma 2 of t. So take 4 is like the optimal way to bound G of t. So up to a constant factor, this thing exactly captures the mean width. Notice that this bound is potentially better than the Dudley bound because you always get an upper bound by moving the soup inside the sum. So I'm not going to prove this, but I'll put the proof of the upper bound in the notes and a reference to the lower bound. And then the proof, maybe I'll say a few words for this at the beginning of next lecture. The proof of Gordon's theorem so there's a recent paper from this summer due to Oimak, or I might be spelling the name wrong. I think we should get out very soon. Oimak, Recht, and Sultanul Khattabi, I believe. Which says DJL with the right parameters implies Gordon's theorem. So we saw that Gordon's theorem implies JL because G of t is never bigger than root log t. What they showed is actually, you can go the other way around. If you have DJL, it implies Gordon's theorem. And basically what they say is, basically take DJL where epsilon tilde is something like epsilon over gamma 2, some constant times gamma 2 of t, which implies that m just needs to be at least log 1 over delta over epsilon tilde squared, which is g squared of t times log 1 over delta over epsilon squared. So they sort of do it in a black box way. They say that if you have a JL distribution with this error, with this kind of error, it implies that you'll preserve all of t. How many dimensions do you need to get, well, this is gamma 2 squared. How many dimensions do you need to get this kind of error? You need 1 over epsilon tilde squared times log 1 over delta. So this implies that m needs to be log 1 over delta over epsilon tilde squared, which is this. But by that theorem, Talleyrand and Fernique, we know gamma 2 and g are basically the same thing. So this is the same thing as g squared of t times log 1 over delta over epsilon squared. And I'll say a few words about, I'll say like, maybe 5 minutes of how they prove this in the beginning of the next lecture, then we'll move on to something else. But it's nice because it says that JL and Gordon are basically equivalent, or DJL and Gordon are basically, well, Gordon implies JL and DJL implies Gordon. Good. It's a slightly suboptimal result just because this time should really be a plus. We know that you can achieve a plus here, but they get with the times. And essentially, the way this works is look at this infinite collection of nets, these S's. You just need to preserve them at different scales, and it implies that you preserve t, basically. Okay. So we'll see a little bit about that on Thursday. Anyway, and then we'll do something else.